Hello again, welcome to another lesson in geometry. Today we are covering section 12-4, angle measures and segment lengths. So we have some vocabulary review here. Underline the correct word or words to complete each sentence for number 1 here. So the student went off on a tangent, that just means you get off topic, when he did not stick to the subject. Okay, a tangent to a circle intersects the circle at exactly 1 point. Okay. So that's this picture. There's our circle, and here's a line of tangent C, or a tangent line, and it intersects at 1 point at the point of tangent C. And then from a point outside a circle, there are 2 tangents to the circle. So here's another circle, here's a point outside it, and we can draw 1 tangent line this way, and 1 tangent line that way. So we always have 2. All right, vocabulary builder, we have a new word. We have secant. Secant is a noun. Related word is tangent. So tangent only intersects the circle once. A secant will intersect the circle twice. So a secant is a line that intersects the circle at 2 points. The word secant comes from the verb secare, Latin verb, which means to cut. So it cuts the circle twice. It also cuts the circle into 2 parts. An example is in the diagram on the right, AB is a secant. But we could also have AB and BA rays, be secant rays, and we can have a secant segment, okay, AB. So write secant or tangent to identify each line. So the first one is a secant, it intersects twice. The second one is a tangent, intersects circle once. And then we have a tangent, intersects once. And then we have a secant, it intersects twice. Okay, happens to also go through the diameter. So is a chord a secant? So this is actually no. You might say, well, what about a secant segment? Well, yeah, but it could extend it on and still be a secant. So this is no. A secant contains points outside of the circle. Okay, where a chord does not. All right, let's flip it over and check out page 2. Theorem 12-13, 12-14, and 12-15. So theorem 12-13 says the measure of an angle formed by 2 lines that intersect inside a circle is half the sum of the measure of their intercepted arcs. So what's going on here is we have 2 lines, and these 2 lines are crossing inside the circle. They don't have to cross at the center, just somewhere inside. And then we can find 2 arcs, first arc from here and the second arc from there. So the arcs that are in between the 2 lines where the 2 lines cross. And then the angles that form those arcs, okay, that correlate with those are angle 1 and angle 2 here. And angle 1's measure is going to equal to half of the measure of the 2 arcs added together. And then number 9 says, hey, what about angle 2? Should it also equal that? And this would be yes. Angle 1 and 2 are vertical angles anyway, so we know they're going to be congruent. And by the transitive property, then we can say angle 2 is going to equal to the same formula that angle 1 equaled. All right, so let me show you what's going on with this in another picture here. So here's a sketch of it. All right, so we have these 2 lines crossing. DC and AE cross and intersect inside the circle. Okay, so I measured the 2 angles. DBE right now is 61.64, as well as ABC is 61, or ABC is 61.64. So these 2 angles in here are congruent to each other. And then I measured the 2 arcs. The red arc IJK is 38.52, and the blue arc FGH is 84.76. So if I did 1/2 times the sum of those 2 arcs, I get 61.64, same as those 2 angles. Okay, so it doesn't matter, the angles are always equal, and then they're also always equal to 1/2 the sum of the arcs that are formed. So if I pick up like H here, or maybe, let's see, C would be easier to pick up, I can move this around and change the angles, okay, same with like E. But no matter where I put it, the angles inside are still equal, and the arcs added up and divided by 2 will also still be equal. Okay, so I can put this D, pick them up, move them anywhere I want, and no matter what I do, I still keep all those angles, and then the half of the sum of the arcs the same. All right, so that's what that first theorem is saying. In our second theorem, 12-14, the measure of an angle formed by two lines that intersect outside a circle is half the difference of the measures of the intercepted angle. So up here, it was the sum of them, and then down here is going to be the difference. So when the point is inside the circle, it's the sum of the arcs. When the point is outside the circle where the lines intersect, it's the difference of the arcs. We want to use the bigger arc minus the smaller arc. So here's a picture of what that means. Okay. Let's see. Cancel. Let's make this big here. There we go. All right, so here's my circle. Oops. Let's move it where we can see it. All right, and somewhere out here is my point that's outside. Okay, so I have my point outside, and inside the circle, let's get our two arcs in the right spot. There we go. All right, so here we go. Our point's outside, and then we have this arc, DEF, okay, the red one, the small one, and we have the big arc, AGH here, okay? So if I take the big arc, the blue one, and subtract the little arc, the red one, and then I cut that in half, I get the same measure of the angle that's out here. And it doesn't matter where I put the angle, okay, as long as I keep my arcs drawn. So I can move my angle up here, and then I got to move D back inside. And then the blue and the red one, subtract it from each other, cut in half, still makes the measure of the angle. Okay, same thing with this. I can move this around, and it still works. My formula works where I take the blue and red one, subtract them, divide it by 2, and I get the measure of the outside angle. So B is the outside angle, and this is what we're finding. So we want to find where two lines intersect outside the circle. It's subtraction of the arcs cut in half. And if you want to find it when it's inside the circle, it's sum of the arcs cut in half. All right. So for 12-14, that's what it's talking about. And you can see out here is angle 1, and that's going to be half of the red and blue put together. And it doesn't matter whether they go through as a secant or whether they cross the circle as a tangent. It still works. So if angle 1's out here, and we have one tangent side of the angle and one secant side for the angle, the blue and red subtracted, cut in half will still be equal to the angle. And the same if we have two tangents, the blue and red subtracted and cut in half will still be equal to the angle. So in the first diagram, the sides of the angles are a secant and another secant. Okay. And in the second diagram, the sides of the angles are a secant and a tangent. So this is secant, this is tangent, and in the third one, the sides of the angle are tangent and a tangent. And it doesn't matter, no matter what we do, the formula will still work. So is the measure of angle 1 equal to 1/2 y minus x equivalent to the same as measure of angle 1 equal to 1/2 x minus y? And this is no, because we need to make the bigger arc go first, and if we don't, then we're going to get a negative number for the measure of an angle, and that's just not possible. Okay, our last theorem on here, theorem 12-15, says for a given point in a circle, the product of the lengths of the two segments from the point to the circle is the constant along any line through that point. So for instance, in case 1 here, this is our point, okay? And we have two distances for the blue part. We have this distance going this way, and we have this distance going this way to touch the circle. And then they drew another one to show that it doesn't matter. So we have for this way and this way. So if we draw lines through that point and we find the distances it takes to get to the circle. Okay, so the product of A times B in case 1 when the point is inside the circle is going to equal to the product of C times D. Okay, so if the point is inside the circle, then doesn't matter. The distances, the products of the distances from the point to the edge of the circle will always be constant. All right, so case 2 is when a point is outside the circle and we have two secants that come across it. All right, so this is a little bit different in the way we write it, but it means the same thing. So if we look down the blue one from this point, it's this far to cross to the circle the first time, so that's W. And where it crosses to the circle the second time is the distance w plus x. Okay, so that product should be equal to any other line that crosses through the circle again from that same point. Okay, so here's our second one, the red one. This distance is the distance to cross the circle the first time. So that's going to be, y here. And this distance from here to here is where it crosses the circle the second time. So that's y plus z. Okay. All right. And then in our last one, case 3, it's a little bit different here. We still have our point. Okay. And the distance for the red one to where it crosses the circle, the first one is y. And the second one is y plus z. That's where it will cross the circle the second time. So y plus z. Now for the other one, when it's a tangent line, it crosses the circle at the same place twice. So first it's t, and then it's t again. So that's where they get t squared from. Okay, so if it's a secant, then we use the two distances, one where it crosses the circle twice. So any secant, whether that secant be inside or outside from the point. So here from this point, it crosses the circle once here and once here. So we use those two distances. But if the point was inside the circle, then we would use this distance going that way and this distance going that way from the point. Okay. So it works the same, but if it's a tangent, it's a little bit different. Okay, on problem 1 here, we have finding angle measures, and it says what is the value of w? So w is the arc measure, and we know that it's formed by this angle on the outside at 70. It splits it into 2 parts. So if we look back at 12-14, it tells us to use that one. So up above, we have 12-14 says the measure of the outside angle, okay, is going to be equal to 1/2 the difference of the big arc minus the smaller arc. So in this case, the measure of our outside angle is 70, and that's going to be equal to the measure of 1/2 times our big arc, which is w, minus the smaller arc, which is 110. All right, so now we're going to solve this equation to find out what w was. So I'm going to say 70 equals 1/2 w minus 55. And then we'll add 55 to both sides to get 125 equals 1/2 w. And then double them, and we're going to get 250. So w is going to be 250. Now that makes sense, because if you think about the two arcs together, this arc is 110. And then this arc uses the rest of the circle. So that's got to be 360 minus 110, which would be 250. So together, the two arcs make up a whole circle, and they should add up to 360. Okay. All right, problem number 2, finding arc measure. Okay, so a departing space probe sends a picture back of Earth as it crosses Earth's equator. Okay, the angle formed by the two tangents to the equator is 20 degrees. What are the arc of the equator is visible to the space probe? So what part of the arc of the equator is visible? Use 20, F and G and the words Earth and probe to complete the diagram below. Okay, so 20 is the angle. Okay, and this is our probe out here. And this big circle is supposed to be Earth. And then this will be F and G. Okay, so it's the tangent lines that are drawn from the probe back to Earth. Okay, and those are the points of tangency. All right, so complete the flow chart below to help us figure out the answer to what is the degree of the arc of the equator is visible to the space probe. So what part of the Earth part? Okay, so let arc FG equal x. That's what we're looking for. So we're going to let this arc, the part that we can see from the probe, be x. Okay. Then FEG is going to be equal to 360 minus x, and that's because the sum of the arc measures has to be 360. It makes a whole circle. All right. So then FPG, the measure of FPG, this guy up here, is going to be equal to 1/2 of the measure of FEG minus the measure of FG. Arc FG. So the two arcs together Okay, that's theorem 12-14. The outside angle is equal to half of the big arc minus the small arc. Okay, then we're going to substitute some things we know. We know the outside angle is 20. Okay, and then we know that the big arc is going to be 360 minus x, and the little arc is going to be x. Okay, and then we'll simplify this to 360 minus 2x. Okay, and then we'll distribute the 1/2. This will give us 180 minus x. Okay, and then subtract 180, or subtract 180 from both sides will give us negative 160 equals negative x. And then divide by negative to both sides, and we're going to get 160. So the arc of what the part of the equator the probe can see is 160 degrees. Okay. So this measure here is 160, and that means over here is 200. All right, let's flip it over and look at our last page. Problem number 3, finding segment lengths. So what is the value of the variable to the nearest tenth in our diagram over here? So underline the correct word to complete each sentence. So the segments are going to intersect outside of the circle. Okay, so write a justification for each statement. So 14 plus 20, so that's the whole length, times by 14, that's this length. So this is where this secant crosses the circle twice. So the distance to the first time it crosses the circle is the green one, and the distance to the second time it crosses the secant is the blue one. Okay, and that should be equivalent to any other one that crosses. So over here, we're going to do the distance to where it crosses the first time, which is 16, times the distance of where it crosses the second time, which is 16 plus x. All right, so this is theorem 12-15, case number 2. All right, now we're going to do some solving here. So we're just going to distribute the 16. So this is our distributive property. Okay. And then we're going to subtract 256 to both sides. So subtraction property of equality. And then we're going to divide 16 to both sides. So that's our division property of equality. And then to the nearest tenth, what is the value of x? That's going to be 13.8. So that's just some rounding at the end. All right, so they solved the equation once they wrote it. All right, so we have a lesson check down here. So as always, pause the video. Okay, welcome back for your lesson check. Let's see what we have here. So in the diagram at the right, it is possible to find the measures of the unmarked arcs. So this is our question mark. Can we do it? So we have this arc marked as 85, and we have this one marked as 45. Okay, so we want to know what are the other two arcs. So you can use the intercepted arcs to find the value of y, and this is yes. Okay, this is theorem 12-13, I think. These two intercept in between. So we could say y is equal to 1/2 of the sum of the two arcs. So 45 plus 85, and that would let us find y. Okay, then you can use supplementary angles to find the measures of angles adjacent to y. Sure, that would let us find this one and this one. We'd also know that that's also the same as y, so we get all those angles. You can find the sum of the unmarked arcs. Yeah, we could do that. We know what they're all going to add up to. Okay, we know that this arc plus this arc should be equal to 360 minus the 85 minus the 45. Okay, but we don't know how much each one is. So is it possible to find the measure of each unmarked arc? This would be no. Okay, we would know an angle. That's good. Okay, but we need to know one of these two red ones before we can find the other one. Okay, so this would be no. The sum of the unmarked angles is not enough information to find the measure of each unmarked arc. Okay, we could find out what they add up to, and we know that if we cut that in half, we would get that angle, but we can't tell how much each one is. All right, so that concludes our lesson today. Oh, and by the way, all these sides in here and this angle outside here doesn't help us in any way either. Okay. All right, so check off the vocabulary words that you understand. So we've been working with chords for a while, circles for many years. Secant and tangent are still appearing again. And then how well can you find the links of segments associated with circles? Hopefully you're in here, but if not, we'll practice some next time and start getting ready for our test that is coming very shortly. See you in class.